So we're now going to take an in-depth look at differentiation of the natural log function. So first of all, let's recall that by construction of the natural log function, the derivative of ln of x is 1 over x. That was by construction of the natural log function, and that is for x greater than 0, of course. Now it's important to note that when you're differentiating ln x, the x here and the x that you're differentiating with respect to must match. So now, if you have something like the natural log of u, where u is a function of x, how do we differentiate this with respect to x? Well, you just have to use the chain rule. So if u of x is a differentiable function of x, then the derivative of ln of u with respect to x is going to be d du of the ln of u times du dx. So this is by the chain rule. And notice that these du's cancel and you recover d dx of the ln of u. So we just get this back. Now, before we cancel them, let's actually employ the chain rule here. So now this piece right here, you notice how the u here and the u here, they now match. And so this quantity right here is just going to be 1 over u, using what we have up here with u in place of the x's. And then we just have to multiply by du dx. And what we get is 1 over u times du dx. And this piece right here is just u prime, of course, and we end up with u prime over u. So that's what the derivative of the ln of u is with respect to x. Now let's consider these two examples here. So for the first example, we want to evaluate the derivative of the natural log of x squared plus 3x plus 1. So following the rule that we have right here, we're going to let u equal the x squared plus 3x plus 1 term, in which case the derivative of this function is going to be as follows. So if the u is equal to x squared plus 3x plus 1, all we have to do is follow this rule, which is an application of the chain rule. And so this is going to be d du of the ln of u times du dx. And that is just going to be, with this term being 1 over u, and this term is going to be 2x plus 3, and we end up with and there is our derivative. Now I went through the chain rule here. You could simply jump straight to this step right here and say that the derivative of this function is just the derivative of u, which is 2x plus 3, over u. But if you're thinking of applying the chain rule, this is how you would do it down here. Now for our second problem here, the u in here looks a little bit complicated. So taking the derivative of this function, which is what we would have to do up here, is a little bit complicated. So what we're going to do instead is simplify this using properties of the natural logarithm. So we're going to write this as, there you go, so we just use the property that the ln of a divided by b is ln of a minus ln of b. And now we can further simplify this as we can bring this 3 down front using the property that the ln of a to the b power is b times the ln of a. So this is going to be, now remember the square root of x squared plus 1. This is the same as x squared plus 1 to the 1/2 power. So we can bring that 1/2 out in front like this. And there we go. Now, to differentiate this, all we have to do is differentiate these two terms and we'll have our answer. So therefore the derivative of the function we want well, that will just be the derivative of this term, which is just going to be 3 times 1 over x. And then the derivative of this term, we're going to have 1/2 times. Now for this piece right here, this is going to be our u. And then just following our rule up here for the derivative with respect to x of the ln of u, the derivative of this term is going to be 2x, that's the derivative of u, divided by u. And then if you'd like, you could simplify this as and then of course just cross multiplying this, we would get alright, that's just cross multiplying, and then this would further simplify as, I'll just put it right here, and there you go. There is the derivative of the function that we had started with. Once again, notice how we simplified first using properties of the natural logarithm, and then that made it much easier to differentiate this function. Notice up here we did not simplify because we can't. Up here we have the natural log of the sum of several terms. There is no rule for simplifying that. Remember, you cannot say the natural log of a plus b is the natural log of a plus the natural log of b. That is not true. So this could not be simplified any further. Now let's take a look at a few more results related to logarithmic differentiation. So let's consider this theorem. It states that the derivative of the natural log of the absolute value of x is 1 over x, and that's true for all x not equal to 0. So in other words, this result holds for all x values that are either positive or negative. If you recall, before we only had the result that we only had this result for x positive, and that was because the natural log of x is only defined for x being a positive number. But if we take the absolute value of x, then this is defined for all x not equal to 0, and then we have this result here. In addition, if u is a differentiable function of x, then we have that the derivative of the natural log of the absolute value of u is still u prime over u. Recall we had a result previously that said the derivative, that this was u prime over u, but we can extend this result by putting absolute values around the u, and we still get the same result. So let's take a look at the proof of this. We're just going to prove this part right here. So now what we're going to do to prove this is we're going to break it into cases. First of all, we're going to consider the case where x is a positive number. So if x is a positive number, notice that the absolute value of x is then just x. So the derivative of the natural log of the absolute value of x is then just the derivative of the natural log of x, and that's just 1 over x. So that case is easy when x is a positive number because the absolute value of x is just x anyway. Now if x is a negative number, it's just a little more tricky. If x is a negative number, notice that we can write the absolute value of x as negative x. For example, the absolute value of negative 3 we can write as negative of negative 3, which gives us back positive 3. So notice the negative 3 here is playing the role of the x over here. So what we can do then is we'll say that the derivative of the natural log of the absolute value of x, we can replace this absolute value of x with negative x right here. And now think of this as being a u of x. And what we do is just use this result up here now, where the u is negative x. So then what we get, I'll just write it down here, this part right here is then just going to be u prime over u, where u is negative x. And that's where u is negative x. And the derivative of negative x with respect to x is negative 1. And u is just negative x. And we get 1 over x, which is what we have written right here. Alright, so that proves it for the case when x is a negative number. So let's take a look at an example here. So for example, let's evaluate the derivative of the natural log of the absolute value of sine x. Well, all we have to do is follow this rule right here. So let's identify what the u is. Well, in this case here, the u is just our sine x function. And so then what we get here is that this quantity right here is equal to u prime over u. And u prime is going to be the cosine of x divided by, and u is just sine x. And that's our answer. And we could simplify that, noting that this is actually the cotangent function. And there we go. Now let's take a look at another concept called logarithmic differentiation. Here we have an interesting example. We want to evaluate the derivative of the function x to the x power. Now, some people might make the common mistake, and this is understandable, if you think back to something like, how do we differentiate y equals x cubed? Well, if you want to differentiate x cubed, of course, what you do is just drop the 3 down and subtract 1, right? And you get that y prime equals 3x squared, of course. However, if we want to differentiate something like this, it is not correct to drop this x down in front and subtract 1 from the exponent. And that's because up here, when we apply the power rule for differentiation, the exponent must be a constant. So that 3, that has to be a constant. It must not vary as x varies. If you think back to the proof of the power rule, you know, when we prove that the derivative of x to the n is n x to the n minus 1, this value right here must be a constant if you think back to the proof of the power rule. So now what we have here is this is not a constant anymore. So we are not justified in using the power rule. So how do we evaluate the derivative here? Well, what we have to do is we have to get that x out of the exponent somehow. And the way you do that is by taking the natural logarithm of both sides. So let's do that here. So if we start with y equals x to the x, we have to get this x out of the exponent. So if we take the ln of both sides, now what we can do is we can drop this x out in front of the natural logarithm, and then we have it out of the exponent. And so this is equal to, like that. Now keep in mind, this y is now a function of x. So let me specify that. That is actually a function of x. And so now what we have is, we have that the ln of y, and that's a function of x, equals x times ln of x. Now what we're going to do is differentiate both sides with respect to x. Now the derivative of this side right here, the y is playing the role of a u, like this up here. So the y is just playing the role of the u. So this piece right here is going to be y prime over y. And the y prime is what we want to solve for. Now the derivative of this side here, we have to use the product rule. So it's going to be x times the derivative of ln x, and that's going to be x times 1 over x, right? 1 over x here. This is the derivative of the ln of x. And then plus ln of x times the derivative of x with respect to x. And then all of this simplifies to 1 plus ln x. Now moving back up here, so what we have is moving this y, multiplying it over to the other side, we end up with y prime equals y times plus ln x. And the y is equal to x to the x power and we have our answer. So this is our derivative right here. This is what we wanted to find. And so there, that is the derivative of x to the x power. Let's try one more example, just so you get the hang of it. Let's evaluate the derivative of this function. So say we want to differentiate x to the sine x power. Well, what we have to do is get the sine x out of the exponent because it's not a constant. So we take the ln of both sides. We get so there I took the natural log of both sides and I dropped the sine x down in front of the ln right away. Now we just have to differentiate both sides here with respect to x. So we take the derivative of both sides. Now this side right here is once again going to be y prime over y. And here we have to apply the product rule again. So sine times the derivative of the ln of x. So that's going to be, and then ln x times derivative of sine. And then we have to multiply this y back over to the other side, and we obtain and we have our answer. Notice that this piece right here, that's the y that we multiplied over to the other side. And so this is our answer right here. So the derivative of x to the sine x power is x to the sine x power times all of this, sine x over x plus cosine x times the natural log of x. And that concludes our discussion about logarithmic differentiation.